Hello everyone, let's analyze. So in the previous lecture, you should have seen an animation of what it means to be Riemann integrable. And it really is a matter of summing rectangular areas. So our goal for today is, when can we be guaranteed that a function is integrable, other than just when it satisfies the definition of Riemann integrability? And for those of you who just can't wait, spoiler alert, it's when a function is continuous on the closed interval a to b, or if a function is increasing or decreasing on a closed interval a to b. Of course, these aren't the only functions that are integrable, but when functions satisfy these conditions, we're guaranteed that they are integrable. So just a reminder of some of the terms from the last video. A partition of an interval a to b is just an increasing set of points, where the first point x naught is a, and the last point, the nth point, is b. The space between these points are subintervals. For example, x naught to x1 is the first subinterval. If I take the supremum of my function over each subinterval and take that to be the height of a rectangle whose width is the length of my subinterval, and I add up those rectangles, then I get the upper sum. Now we can see here that if the function is actually integrable, then of course the upper sum is greater than or possibly equal to the integral itself. Now, of course, if a function is continuous, we can replace supremum with maximum. But to keep our definition as general as possible, for now we'll stick with supremum. Now, if instead of taking the supremum over each subinterval, I took the infimum, again, I can think in my head the minimum, and in fact, it would be correct. I'd be guaranteed to have a minimum on each subinterval if my function were continuous. So to be general, we'll keep the word infimum. So if I took the infimum over each subinterval to be the height of the rectangle and the width to be the length of the subinterval, then I'd get the lower sum. And of course, we can see that if the function is integrable, the lower sum is less than or equal to the integral. And of course, we should be able to deduce by now that the lower sum is always less than or equal to the upper sum. And just so I can introduce a little bit of shorthand and a reminder so that we have all the definitions on the same page, a partition of the interval a to b is an increasing set of points where the first point is a and the last point is b. The upper sum is the sum of rectangular areas where the width of each rectangle is the width of a subinterval, and the height is the supremum of f on that subinterval. So for our shorthand, we're going to call delta xj the length of the jth subinterval, and capital MJ the supremum of f over that subinterval. That should save us a bit of writing. Similarly, for the lower sum, which is the sum of rectangles whose heights are the infimum over a subrectangle, which we're going to write lowercase mj, and again we'll keep that same width of delta xj. So now we have all of our definitions here on one page. Some more shorthand. When I say the infimum of all upper sums of f over all partitions, I'll write it this way. So that means, again, of every upper sum over every possible partition, I want the infimum. Now, we can think in our minds the smallest upper sum, even though it's possible, probable even, that that's like thinking the smallest number in the open interval 0 to 1. Of course, there isn't a smallest number in the open interval 0 to 1, but there is an infimum 0, the greatest lower bound. So, but when we're conceptualizing these ideas, it is useful to think in our mind of all the upper sums, the smallest, if there is one. And if there isn't, then we mean the greatest lower bound. We will also write that as the integral from a to b of f of x with a line over the top, so that we mean the infimum over all upper sums. So we'll have really kind of two shorthand ways of writing this term here in the middle. When I say the supremum of all lower sums of f for every partition p, I'll just write it supremum over p, which is also written as the integral with a line at the bottom, sometimes expressed as the lower integral. So to remind ourselves of what it means to be Riemann integrable, again, we've seen this definition in the last video, but let's just remind ourselves. If the infimum over all partitions of every upper sum equals the supremum of all lower sums for every partition, then we say our function is Riemann integrable. Furthermore, the integral is equal to the infimum of upper sums, which of course is equal to the supremum of lower sums if the definition is satisfied. Okay, and now we're ready. So we'll need a few lemmas in order to get to our two punchlines, that continuous functions on a closed interval are integrable, and increasing or decreasing functions on a closed interval are integrable. So the first lemma says, if a function maps the closed interval a to b to r, if p prime is a refinement of the partition p. Now, what do I mean when I say a refinement? Well, when I say a refinement, what I mean is that p prime, remember, p prime is just a set of increasing points. P prime contains all the points of p. In other words, if I start with the partition p and refine it, I'm keeping all of my partition points and I'm adding to it more partition points. And that's a refinement. So if I refine a partition, then I get a greater or equal lower sum, and I get a less or equal upper sum. Now let's think about why that's true. Let's consider the most unrefined of partitions, where their partition where n is equal to 1. In other words, where x0 is a, x1 is b. Let's consider the upper sum. In that case, the upper sum is just the area of a single rectangle whose width is b minus a and whose height is the maximum or the supremum of the function. Any refinement, and of course every partition is a refinement of this because every partition has to contain the points a and b. So every partition, which is a refinement, must give me a smaller or equal upper sum. Now, let's prove it in general. So let's number our partitions. So we have some original partition P, we call it P0. Let's add a single point to P and call it P1. Let's add a single point to P1. Let's call it P2. And of course, the point we're adding A to is not in P1, right? It's a new point. And we'll continue in this way. We'll add a kth point to pk minus 1, and we'll get pk. At some point, we'll arrive at our refinement. In other words, there's an L for which PL is equal to P prime. Right? L is just how many more points our refinement has than our original partition. So let's consider the case that we add 1 point to a refinement. So we're adding AK to the partition PK minus 1. And let's suppose that AK is between XK and XK plus 1. Of course, it's not equal to XK or XK plus 1 because I'm adding a new point. So let's consider the lower sum. Now, we're only going to prove the lemma for the case of the lower sums, but the idea is the same for the upper sums. So the lower sum is a sum of rectangular areas. Height, infimum of F over my partition, width is my subinterval length. Now, remember, AK is between these 2 points, whose distance between them is given by delta xk. So let's analyze that term. Remember that delta xk is xk plus 1 minus xk. So I just replace the delta xk with what it's equal to, which is the subinterval length. Now, let's take that term and add 0, but with style and purpose. We're going to add AK and subtract AK. Then let's distribute MK. Now, remember what MK is. MK is the infimum over that interval. The interval from xk to xk plus 1. But now I'm multiplying it by the length of a subinterval of the original subinterval. Remember, AK is between xk and xk plus 1. In fact, as you're following along, it probably would be a good idea to sketch a picture. Now, if I replace the infimum of F over xk to xk plus 1 with the infimum from AK to AK plus 1, I have to get something that's either the same or bigger, because the interval AK to xk plus 1 is within the interval xk to xk plus 1. So because I have a smaller subinterval, F, the infimum, is either going to be bigger or it's going to be where it was before. Similarly, with the interval xk to ak, because that's a subinterval of xk to xk plus 1, the infimum has to be either bigger than it was before or the same. Well, what this is less than or equal to, in other words, this line here, is precisely the lower sum of the kth partition. In other words, by adding 1 point to the k minus first partition to get the refinement pk, I have either increased or kept the lower sum the same. So, if I begin with the original partition and add a single point, I must be bigger or the same. That's what I just proved. And if I add 1 point to that, I must be bigger or the same. So forth and so on until I get to the nth or the final refinement. So, the lower sum of the original partition must be less than or equal to the lower sum of the refinement. And as I mentioned before, the upper sum case is similarly proven. Now, suppose I have a function from the closed interval a to b to r. For any two partitions p and q, the lower sum of f over the partition p is less than or equal to the upper sum of the same function over a different partition q. Of course, it's clear that if p and q are the same partition, of course the upper sum is greater than or equal to the lower sum, because I would have a sum of rectangles that have the same width, but of course the upper sum has greater heights because the upper sum takes the supremum as the heights, the lower sum takes the infimum as the heights. But even if I have different partitions, I still get that inequality. And for the proof, we're going to use the previous lemma. If I take p and q and put them together, well, then I have a refinement of both p and q. That means the lower sum of the refinement, p and q together, is greater than the lower sum of just p. And that's less than or equal to the upper sum of f over the same refinement, right? We just mentioned y. And because that upper sum is a refinement of q, it's less than or equal to the upper sum of f over the partition just q. And we've proven our result. Now let f map a to b, a closed interval, be bounded. Then the supremum over all lower sums is less than or equal to the infimum over all upper sums. Again, a loose way to think about this is that the largest lower sum is less than or equal to the smallest upper sum. Again, we're being a bit loose because it could be that there is no smallest upper sum, but there may be an infimum. And of course, the idea is straightforward. Since every element of the set of all lower sums for all partitions is less than or equal to every element of the set of all upper sums for all possible partitions, the least upper bound of all lower sums is less than or equal to the greatest lower bound of all upper sums, which is exactly what we wanted to prove. And now we've come to the first of our finales. Let f map the closed interval a to b to r be continuous. Then the function is Riemann integrable. Now, our proof is we're going to show that the infimum of the upper sums equals the supremum of the lower sums by showing that for any epsilon, there's a partition P for which the difference of the upper sum and the lower sum is less than epsilon. If we can show that, then we've shown that f is Riemann integrable, because this implies that the infimum of all upper sums equals the supremum of all lower sums. Now, we should, given our Real Analysis 1 training, know precisely how to prove that statement. So our goal is to show that this is true. Now, since f is continuous, and the closed interval a to b is both closed and bounded, then the domain is compact, meaning f is uniformly continuous. So let epsilon be an arbitrary positive number. By the definition of uniform continuity, there exists a positive delta, so that if x and y are in the domain, and are within delta of each other, then f of x minus f of y is less than epsilon over b minus a. Why epsilon over b minus a? Well, we're going to see shortly that it'll give us precisely what we need. Let P be a partition so that every single subinterval has a length less than delta. Then the upper sum minus the lower sum is basically a sum of rectangles whose width is the length of the subintervals, but whose height is the difference between the supremum and the infimum. While the supremum minus the infimum is the same thing as the max minus the min, right? Because our function is continuous, therefore it's uniformly continuous. And if it's uniformly continuous, it has to achieve a max and a min on a closed interval. And the difference between the max and the min, because x minus y is less than delta, the max minus the min has to be less than epsilon over b minus a. So we replace this with epsilon over b minus a and the equals with the less than or equal to. In fact, we could have replaced it with a less than. Now notice that epsilon over b minus a is a constant. If we factor it out, then we're just summing all the subinterval lengths. Well, if I sum all the subinterval lengths, I just get the length of the whole interval, b minus a. And we have our epsilon, which was arbitrary to begin with. So we've proven our theorem. And now we come to the final finale. Any increasing or decreasing function defined on a closed interval is Riemann integrable. So suppose f is increasing. The proof for a decreasing function follows similarly, so we'll just prove it for the increasing case. Our goal is to show that for a sequence of partitions, Pn, the limit as n goes to infinity of the difference of the upper minus lower sums for these sequence of partitions is 0. Of course, if we remember the precise definition of what a limit is, we realize that this goal is precisely the same as the goal in the previous proof. So let Pn be evenly spaced partitions. So the subinterval length is the entire interval length divided by n. Then the difference of my upper and lower sum is the supremum minus the infimum over each subinterval times my subinterval length, which is the same for each subinterval. Because it's the same, we can factor it out. And because my function is increasing, the supremum must occur on the right, f of xk plus 1. The infimum must occur on the left of the subinterval, f of xk. So let's add up those differences. I get f of x1 minus f of x naught, f of x2 minus f of x1, f of x3 minus f of x2, etc., until the last interval. Well, notice I have a f of x1 and a negative f of x1. They cancel. F of x2 and a negative f of x2. They cancel. F of x3 and a negative f of x3. They cancel. But you don't see the negative f of x3. It's hidden somewhere deep down in those ... dots. And we can continue on with our cancellation, and we're left with just f of xn and negative f of x naught. Of course, that's f of b minus f of a times b minus a over n. F of b minus f of a, that's a fixed amount. B minus a, that's a fixed number. If I divide that fixed number by n and take the limit as n goes to infinity, I approach 0, which means I've proven my goal, which is equivalent to proving integrability. That's all for today.